Yes, yes, of
Kiran?
course. Yeah.
Okay, fine.
Yeah,
Thank you.
I started the recording.
Good. Thank you. So, good evening and good morning for some of you from the other continent. And, I mean, whatever part of the day is for many of you. So, warm welcome to this InSIS webinar series 2023. And today we have a lecture on fracture and size effect in the compressive failure of fiber reinforced composites by Professor Kedar Kirane from Stony Brook University in New York. Uh, his biodata reads like this. He is currently an assistant professor at the Mechanical Engineering Department at Stony Brook, New York. He focuses on characterizing, understanding, and predicting the fracture and scaling behavior of various conventional and advanced composite materials. These include brittle materials, fiber reinforced composites, polymer nanocomposites, geological and cementitious materials, and soft materials. His research combines experimental, computational, and theoretical approaches. The overarching goal is to develop reliable predictive capabilities and sound scientific basis for safe structural designs in various engineering applications. Uh, Kiran obtained his PhD from the Northwestern University, joined the Mechanical Engineering Faculty Department at Stony Brook in 2017. He holds a MS degree from the Ohio State University and BS from the University of Pune in India, all in mechanical engineering. Prior to joining Stony Brook, he worked in industry as a finite element analyst at Goodyear Tire and Rubber Company, and later as a senior research engineer at ExxonMobil. His research is supported by several agencies which are prestigious, Department of Defense mostly, and from ASME. He's a recipient of the 2020 or Early Career Research Award by the ASME's Materials Division and 2019 Department of Defense ARO Young Investigator Award and the 2018 Hathorn Weight Research Initiation Grant by the ASME's Applied Mechanics Division. With this few words of introduction, I will now request Professor Kiran to go ahead and deliver his talk to the InSIS community. Professor Kiran, please.
Uh, okay, Raghu, thank you so much for the introduction and also the invitation to this, for the seminar. And I'm very happy to present this. And yeah, I look forward to, discussion afterwards. So let me share my screen. Okay, so it's visible, right?
Yes, visible. Yeah.
Okay. All right. So hi, everyone. So the topic of my presentation today is a fracture and size effect in the compressive failure of fiber reinforced composites. And I do want to acknowledge, a lot of the work by my two PhD students, coincidentally, both female and both from China. The first is on the left, Dr. Jing Xu, who graduated in 2021, and her work is being continued by Miss Wan Ru on the right, who is in her second year of her PhD. And a lot of the work is actually funded by grants from one from the Navy and mostly from the Navy and some from the Army as well. So, right, let me get started. So we all know that we are today surrounded by fiber reinforced composites in many applications, in, like wind turbines. Uh, Here we show that in the Boeing 787, actually 50% by weight is actually composites today. Uh, so a lot of aircrafts in the space, in the space science field, also there are a lot of composites used uh, in automotive industry, in, boats, recreational applications, defense applications. And the main reason for that is the composites are very lightweight. At the same time, they are strong and stiff. So they have excellent mechanical properties, which has led to their widespread application in all these various fields. But the main thing to realize is that we have to understand the fracturing behavior very well, and not only understand it, but also be able to predict it, so that we can avoid, failures. And a recent example which may resonate with everyone is this recent failure of the Ocean Gate, Titan submersible, which was made from a carbon fiber reinforced composite mainly, and it actually, you know, uh, ended up like a big disaster. Several like people died and so on. So these are the things that need to be avoided. At the same time, we have applications where actually fracturing is desired. For instance, this in this application, this is called a crush can, composite crush can, which is used in automobiles. It is often placed behind the front bumper, and in the event of like a accident or something, the crush can crushes and absorbs the energy of impact by fracturing. So in this case, we do want it to fracture as much as possible. So in for both these kind of applications, understanding and predicting the fracture is very, very crucial. So a little bit more about the Ocean Gate. There are many articles out there in the media, and there's a lot of speculation about what went wrong. So I will just briefly try to discuss what were the main points here. So in this design, it was a little bit of a new design or a new concept where conventionally these kind of vessels are made from a titanium alloy, and the company Ocean Gate, they decided to now make it with a carbon fiber composite. So the overall structure was that there is a main cylinder at the center, made from the composite. Of course, the matrix was epoxy and the reinforcement was carbon fiber. And then there were two titanium end caps, and then the overall shape was like this, as shown here. Now, a lot of people believe that the problem with this design is that while composites are great for many applications, which involve mainly tension, under designs where most of the stress is compressive, they may not be a great choice. So to explain that a bit, you can view the image on the right. This is like a pressure vessel. So if there is pressure inside, everything is under tension, like the structure, the pressure vessel is under tension. And then for these applications, composites work great. They are lightweight, they have high tensile strength, no problem. But if you replace from inside to outside, like shown on the left, which was the case with the Ocean Gate, the entire structure is under some kind of compression, not uniaxial, but multi-axial compression. And that is often a limiting factor for composites design, because they consist of these long fibers. So when these are long, when they're compressed, they tend to fail by a micro buckling instability. And that's what I will talk about mostly today. So many people believe that this could have been the failure mode for the Ocean Gate, the compressive failure of the cylindrical hull of the submersible. Of course, personally, I'm not sure. It is all speculation at this point, and there could be many other possibilities. Uh, Delamination could be happening between the layers and growing by fatigue. These two dissimilar materials were joined by a glue, and the under moisture the glue could have potentially degraded. The polymer could have been degraded due to potential moisture ingress and so on. So there are many reasons, and actual forensic analysis would help. But one of the points that has come forth during this incident is that the compressive failure of composites is very an important consideration, and that we need to consider, designs should consider fracture mechanics, size effects, and various other effects like crack parallel stresses and so on. So this is what kind of motivates maybe today's talk, in hindsight, the compressive failure of composites. So so the thing to realize is that composites are highly heterogeneous materials. Essentially, they consist of two materials combined, like the matrix and the fibers. And so these are some micrographs showing the heterogeneities in the microstructure. You can see uh, maybe on the right that it's of within one layer of the composite, there are many of these fibers, and I guess micrometer order is the size of these fibers, few microns. Now, composites generally are made into like lamina, like layers, and then they are stacked with different orientations. So each layer is, if you think of it, most common is a unidirectional lamina where all the fibers are running in one direction. And then that makes it very, very anisotropic. So in applications, if you want to mitigate the anisotropy, it is common to, use layers running in different directions as shown here, for example, 0, 45, minus 45, 90. And so overall, then this stack, which is called a laminate, has some kind of quasi-isotropic behavior. But this layering also leads to another kind of, heterogeneity because it's still joining of dissimilar, layers. So there are several length scales involved from all the way from the individual constituent level, where there is matrix and fiber, to a single layer, to a stack of layers, which is then used in structures. So an important thing to understand is how the failure happens, and two, how it scales, like how it transitions when we go from smaller length scales to larger length scales. So one important point, or probably the most important point in understanding this scaling, is the so-called quasi-brittleness of composites. Now, failure can be of mainly two types. We all know that it can either be brittle or ductile. And when it is brittle, we kind of know that at let's say there is a sharp crack, then at the tip of the brittle crack, there is damage which is confined to almost a point. So it's this zone where there is damage occurring is negligible. And for ductile materials like metals, there is this plastic zone which is not negligible in size. But there are quasi-brittle materials such as concrete, rocks, and also fiber-reinforced composites, where there is a damage zone which develops at the tip of a crack, and its size is not negligible in comparison to the size of the specimen itself. So, understanding this process, this is called fracture process zone, as I'm sure you all know. The process zone size is usually more or less a constant. So depending on the length scale that we are operating at, the role played by the process zone increases or decreases in importance. So for instance, for very small scales, probably everything is the process zone. So then it is extremely important. And for very, very large sizes, the process zone is negligible. So then the behavior can be classified as actually brittle. And in this intermediate range where we are maybe in the laboratory dimensions, the process zone is of a moderate size, but still not negligible. And so it plays an important role. And so understanding this transitional role played by the process zone is very important in not only modeling it, but also in characterizing the fracture behavior. So essentially the behavior depends on the length scale. Larger sizes are more brittle. And so the scaling from labs to structural size is very tricky. Now, one of the things that happens with changing size is that the stability of the post-peak behavior changes. For example, smaller specimens are often more stable in the post-peak region, and then larger specimens become more unstable. And there is a very important concept called the size effect law, which basically says that larger structures have smaller strength, nominal strength. Okay, this is not the material strength. Material strength is a constant, but the specimen strength, which is the total load divided by some kind of nominal area, that decreases with increasing size. And now this is also the prediction of linear elastic fracture mechanics, of course. But if you consider linear elastic fracture mechanics, which applies to purely brittle failures, the scaling of strength versus the size D in plotted on this will show like almost a linear plot with slope of minus half. But what happens because of the process zone is that the scaling, it deviates from this straight line. And this deviation is actually described by this empirical law, which is called size effect law, which was first developed by Professor Bazan, who was also my PhD advisor. And this is the well-known form of the size effect law, where sigma n is the nominal strength of the specimen, and d is the size of the specimen. And it has two constants. One is sigma 0, which kind of represents the strength at 0 size, like when d goes to 0. And then d0 is like a length scale parameter, which is related to the size of the FPZ. So when you have a non-negligible FPZ or process zone, you have this kind of transitional behavior of the strength size effect. And when the specimen size becomes really small, this size effect vanishes. So understanding the size effect is really, really important for most materials, including composites. Now, a little bit more about this size effect law. This is basically how the size effect law looks like, where the strength decreases with size, and in this intermediate region, a length scale has to be introduced. It is not self-similar. And then at very large sizes, it becomes what LEFM or linear elastic fracture mechanics describe. Now, an important consequence of this is that if you are in this region, if your sizes, the x-axis is size D here, if you are somewhere here, and if you test the specimen in the lab for fracture toughness, you will actually see that the fracture toughness becomes size dependent, or it appears to be size dependent. And this can easily be seen by just rewriting the size effect law in terms of the fracture toughness. And you can see that this becomes a size dependent equation for Kc, which is the fracture toughness. And it actually increases with size. And only for very large sizes, it kind of becomes constant, which is what fracture mechanics tells us, that fracture toughness is a constant parameter. So if you do a test for a size somewhere in this region, intermediate region, that fracture toughness will not be applicable to large sizes or small sizes. And so it is crucial to understand the scaling, and then to also understand what is the total or the large size true fracture toughness. So characterizing the size effect is very useful in identifying the size of the process zone, for what sizes the linear elastic fracture mechanics can be applied, and the true fracture toughness can be calculated using these equations, where these parameters sigma 0 and d0 are the parameters of the size effect law. So yeah, so this is the one of the main points, and I'm not sure if several applications do consider this this scaling effect in the fracture toughness. So this is one of the main uh, areas of research today in composites. Now there are other size effects also. For instance, there is something called type 1 size effect, which occurs in specimens failing in the presence of a stress gradient. Then there are size effects in fatigue crack growth also. They are very well established for concrete, but they have not been studied for composites at all. Then there are size effects in the probabilistic distributions of strength, and these are the ones that I will not really talk about. But when someone says size effect, I think this is probably the most talked about size effect, the type 2 size effect, which occurs in when in the presence of a sharp crack. So yeah, so that is one of the main points today I want to make, is that this understanding this size effect is quite crucial, especially when you have various heterogeneities and you scale up from the lab to the structural scales. Now, coming back to the composites, they are, like I said, very, very heterogeneous, and because of their arrangement, like how the fibers are, they have a large variety of failure modes, which depend on the direction of the load applied. So for example, if you have a single layer or lamina subjected to tension, it is a tensile failure, and it occurs by a lot of these fiber breaks, okay, as shown here. On the other hand, if it is a compressive load, the failure mechanism is completely different, and it occurs by a formation of a fiber kink band, which is I will elaborate that more on the next slide. Uh, there is also, of course, overall layers can separate within a laminate, so that is called delamination. And there can be transverse tension compression, which causes cracks to grow like this, as shown on the top. This is a cross-sectional view of the composite. There is transverse compression, which causes like an inclined shear crack. And then under compression, there are actually many modes possible, like shear failures, interfacial failures, fiber crushing, interlaminar failures, and kink band failures. So this fiber kink band is one of the most commonly observed failure modes under compression. Now, I should note that each of these mechanisms actually implies the quasi-brittleness that I was speaking of on the previous slide, that each of these mechanisms will probably be quasi-brittle and exhibit that kind of size effect in the nominal strength and also in the fracture toughness corresponding to that failure mechanism. Okay. So all said and done, one of the main failure mechanisms under compression is actually these fiber kink bands, and that is what I will mostly focus on today. So these kink band failures in composites, they actually happen because of it's a two-scale phenomenon. Okay, it's a multi-scale phenomenon, and it is quite complex. And characterizing it and modeling it both are quite challenging. So what essentially happens is, in the simplest terms, fibers are very long and slender, and in the composite there is polymer around it, so it kind of holds everything together, the polymer. But usually there is some kind of misalignment between the fiber direction and the loading direction. Okay. And so because of this, what happens is locally somewhere in the matrix, it gets damaged under shear. And when there is shear damage in the matrix, the fibers kind of lose their support from the adjacent polymer. And this triggers or it enables like a micro buckling type instability in these fibers. So first the fibers will bend a little bit like this as shown here. And then because the fibers themselves are quite brittle, they will kink. And they will kink at two locations, because if you imagine a fiber bending like this and it will come back to be straight. So there are actually two inflection points, if you note. And so then they will kink. So this kind of band will develop and this is called the fiber kink band. It happens only under compression. Okay. And sometimes multiple kink bands can also develop depending on the geometry. And the key characteristic is that when the kink band happens, like this happens at peak load, the kinking, the load drops, and then the load actually becomes constant at some non-zero value. So it never goes to fully zero like in tension. When complete failure occurs under tension, the load goes fully to zero. But under compression, it doesn't. And this is called the residual stress. It's often like plateau. And it represents basically the frictional sliding which occurs in the kink band. Okay. And that's a quasi-plastic type behavior. Of course, eventually it will fully break, but it is a very long plateau. Now, the strength at which this happens, the compressive strength, is usually lower than the tensile strength. But the compressive failure also has this prolonged plateau, so it can actually dissipate a lot of energy by compressive failure also. Now, physically speaking, what happens during this phase is that this band becomes broad. Okay, it broadens, and it is a quasi-plastic process. Another point is that it can happen in various directions depending on the properties of the matrix. Okay, it can be in plane, shown like this. So the kinking is in plane or out of plane. A lot of observations actually suggest that if your loading angle is small, the preferred mode is out of plane, and then at higher angles of loading with respect to the fiber, you can observe in plane kinking. So there are all these features involved in this failure mechanism. It's a two-scale effect because it is triggered by matrix inelasticity. It involves fiber microbuckling. So there is a lot of local rotation. So in that sense, it is also a strain localization problem, except the localization is interesting here because this is all shear deformation in the kink band. And outside the kink band, it is all compressive strain. So the localized region is undergoing shear, while the outside region is under compression. So then there is all this two scale effect. The localization is there. There is friction and sliding within the kink band after it forms. And overall, its behavior is actually like a shear crack. So it is similar to, but not the same as a mode 2 crack. And so this also is a quasi-brittle mode of failure, and it leads to a size effect on strength. So, so to be able to predict this in models, the model needs to, account for all these in a meaningful way. So today I will talk about a model that we have developed recently to, capture these kink band failures in composites. So the approach that we adapted is continuum damage mechanics. Now in literature, you will find many models to predict, fracture. There is, of course, starting with the basic, the cohesive crack model. There is XFEM, the extended finite element method. Of course, there is damage mechanics, continuum damage mechanics that we have chosen. There is the phase field model and so on. But for each one has, its own pros and cons. But as far as the compressive failure of composites goes, by kink band formation, the damage mechanics approach has been probably the only effective way of modeling it. One of the main reasons is that the direction of the kink band is not known a priori. So it has to be a prediction from the model. And so this approach is most relevant to this kink band failure. So what essentially happens in this approach is that we introduce a state variable called damage variable D. So when the D is 0, it implies that the material is undamaged, and it slowly evolves to a value of 1 when the material is fully damaged. And the failure is kind of smeared. So if this is a crack, it is represented by a band of smeared damage. And in this band, the D will go from 0 to 1. And when it goes to 1, its stiffness is lost. So essentially, the formation of a crack is likened to the loss of stiffness of that material. So it's smeared in a region whose stiffness is lost. Okay. Now, the benefits of this approach is that it can automatically capture initiation of cracks, propagation, branching, merging, interactions, and there have been several applications. I need not show it, but I have shown a couple of them here. And importantly, it can capture the complete triaxial state of stress. So you can have complicated constitutive models, and it merges well with this damage mechanics approach. And that is especially important for anisotropic materials when multiple damage mechanisms exist. But the challenge for this is you need to define the damage variable for each failure mode separately, and it leads to a damage tensor, and it becomes very phenomenological and complex. So often for composites, it has been discussed that an approach which handles individual mechanisms separately probably is more convenient, and it is more conceptually clear. And for these kind of approaches, a very effective strategy is to use these constitutive models for microplane models. This was first developed for concrete, but it is a very effective strategy for heterogeneous materials exhibiting multiple failure modes. So I'll discuss that very briefly, or like very soon. This is the approach that we also adapted. So developed like a new kind of microplane model within this damage mechanics framework for kink band failures. Now, before I talk about the model itself, this is an important topic to the regularization or the length scale, which is needed to capture this softening damage. So I'm sure we all know that whenever we capture softening, the results are always going to be mesh dependent, because if you have localization, it will localize in the band of, let's say, one element, one row of elements, and the rest will unload. So if your element size keeps decreasing, the localization will keep happening in a smaller and smaller region. And so the results become mesh dependent. And this is a well-known problem. And the way to overcome this is to introduce some kind of length scale to the model. Now, the simplest way to do that is actually make the energy dissipation per unit area a function of the element size. So if you look at this plot, stress versus strain at a single material element, single material point, this area is, let's say, small gf, which is energy dissipated per unit volume. We can relate it to the fracture energy of the material through a length scale h. Okay, so gf, big gf is actually h times small gf. Yeah, and this h, if we can make it equal to the element size, then that means that if we change the element size, we will have to adjust the stress strain law so that the big gf doesn't change. So this kind of element dependent adjustment of the post peak softening law, this concept is called the crack band theory, and it is often used in conjunction with this continuum damage mechanics approach, this mirrored cracking approach. And what it does is basically makes the element size as the length scale. So this is one illustration here. If basically what it shows is the stress versus strain shown in the on the right schematically, its slope will change with changing element size. So the larger element size will have a steeper slope. Okay. Now, of course, the simplest strategy is to calibrate the model with one element size and then not change that size for all the simulations. Then you can be sure that this problem itself doesn't occur. And that is what we did. But if the element size has to change, then the damage post peak has to be adjusted accordingly so that the energy dissipation does not change. So this is the simplest way to incorporate the length scale to get rid of the mesh dependence problem. And this is called crack band model. And of course, it works for local damage models. There are other approaches, of course. There is gradient damage models, non-local damage models, but they are maybe more complicated. And this is the simplest approach, which is what we adapt. Now, I do want to say that this is a different length scale than the D0 from the size effect law that I mentioned earlier. The D0 from the size effect law is related to the length of the fracture process zone, whereas this H is the width of the process zone, and the width needs to be incorporated in the models to get rid of, the mesh dependence issue. Okay. All right. So going back to the constitutive model, first I will just give a brief overview of what this microplane model concept itself is, and then I will discuss how we adapted it to compressive failures of the Kink pad failures. Now the concept is very simple. In usual continuum damage models, the strain tensor is related to the stress tensor through the fourth order stiffness matrix CIJKL. Now that becomes very complicated when you have several damage mechanisms active at the same time. So in microplane models, what is done is you imagine that at a given material point, there are several microplanes. These are imagined planes within the material microstructure. And this is kind of analogous to crystal plasticity type models used in metals, except in crystal plasticity, the slip planes are well-defined planes, whereas these microplanes are like randomly oriented. And then what is done is you project the strain tensor onto these microplanes and you get then the strain vector. And you define the constitutive law corresponding to individual damage mechanisms in terms of these stress strain vectors. Now, because these are vectors, it becomes very easy to define various damage mechanisms like tensile cracking or frictional slip, local shear, and things like that. And then once you get these stress vectors, you can use the principal of virtual work, or alternatively, we will use strain energy equivalence to get recover the stress tensor back. So by introducing these two length scales within the model, it becomes very intuitive to define various damage mechanisms. All right. So basically the structure goes like this. You project the macro strain onto various microplanes. And this is, of course, for concrete, but we adapted this approach to composites, which I will show later. So you get these strain vectors, one normal strain vector and two shear strain vectors. Then using whatever constitutive law, you get the stress vectors, and then you homogenize these stress vectors using principle of virtual work to get the sigma ij, which is the stress tensor. And so for doing this, you need to assume some kind of volume. So you imagine that one material point is basically a sphere. And so this integration occurs over the surface of the sphere. Now, this approach of assuming that it is a sphere, it works for isotropic materials because the microplanes are then oriented randomly. And so when you homogenize everything, you get like a isotropic response. So obviously this approach won't work for composites. So what we did was we developed a new kind of microplane model. It is the cylindrical microplane model. So instead of the sphere, we introduced a cylindrical arrangement of these microplanes. And all of these are imagined microplanes at a given material point. Okay. So if you imagine one unidirectional lamina, which has fibers running in one direction, we assume that a cylindrical system of microplanes exists, which essentially consists of several planes along the surface of the cylinder and one plane which is lateral, okay, like this. So then what we do is instead of the principle of virtual work, we define the strain energy density at a point. And what it can be done is by introducing three mutually perpendicular microplanes at that point instead of many, just three mutually perpendicular ones. And we can show that the entire strain energy density of a transversely isotropic material can be represented by three microplanes. So we showed this in 2016 Journal of Fluid Mechanics paper, uh, where we developed this so-called microplane triad model. So that this is called microplane triad, three mutually perpendicular microplanes. So in the cylindrical model, which we recently developed, we basically adapted this concept. So the transverse plane of the cylinder is similar to one of these planes of this triad. And then the rest of the cylindrical microplanes are then equivalent to the remaining two planes of this triad. So using this, and I'm probably going to skip all these equations because in presentations, anyway, it is a little hard to grasp all these equations. But these A1, A4, A5, A7, all these constants are basically related to the elastic properties of the lamina. And these are all the strain vectors, epsilon n, epsilon m, and so on. And what you can then show is that if you relate the strain, the first row is the strain energy density from one of the planes, and the second and third are the other two planes. If you equate that to the strain energy density of the cylindrical system of microplanes, you can obtain the moduli which operate at the cylindrical level. So you can calculate the microplane level moduli, which are different from the material's elastic properties. But if you implement this in as a cylindrical system and you homogenize it, you recover back the transversely isotropic response of the composite. So, and then again, like to briefly show, these are A1 through A9 are the various properties, elastic properties of the composite. Okay. So this is the framework of the cylindrical microplane model, where you, instead of a sphere taken for concrete, for composite, you take a cylinder and then you project a strain tensor onto these cylindrical microplanes, obtain the stress vectors, and then calculate the strain energy density. And using that, you can calculate the stiffness tensor to get back the stress tensor. Okay, so that is the overall approach. And how we then capture the kink band formation is as follows. So the hypothesis is that in the kink band, it is all shear localization. And that shear is parallel actually to the fibers. A lot of it is parallel to the fibers. So because we have this cylindrical microplane system, we have easy access to the shear acting on the cylindrical microplanes. So, and we also have shear acting on the transverse n plane, right? The transverse plane. So what we do is we just define a simple damage law, which is driven by the shear acting on the cylindrical microplanes and the n plane. And we use that damage to capture the overall failure of the composite. Okay. So that is one feature where we have simple damage laws on the cylindrical microplanes and also the transverse microplane. And the very important key feature is the orientation of the cylindrical system of microplanes. So imagine that, let's say the kink band is developing in plane. Okay, so we can imagine that overall loading is along the x direction, and then one direction is the fiber direction. There is often usually a initial misalignment angle theta I. So any local shear will add to the theta and will end up involving more rotation. This rotation will increase further the shear and it will keep accumulating. So this is what leads to the shear localization. So in our model, we basically calculate this rotation and calculate this shear. And in each time increment, we solve for this angle. And once we solve for this angle, the system of microplanes is then rotated accordingly. So in each time increment, the orientation of the cylinder is changing with local shear. So this is for the in-plane system. There is also the out-of-plane possibility. So we can do the same for the out-of-plane also. So this is a key feature here. Uh, Calculating local shear and then adding it to the initial misalignment angle to keep increasing the local rotation of the fiber. So, and then we have damage loss on the cylindrical microplanes and the transverse planes. We actually have two versions of the model possible. One is if the matrix behavior is brittle, we can capture it using a simple linear softening law, which is again, it has to be driven by shear, okay, because locally the failure is being caused by shear. Now, if the matrix behavior is ductile, we can have a trapezoidal damage law where there is some kind of plateau and then softening. So you can see that this damage law is actually very, very simple. There is nothing complicated about it. It is just damage driven by local shear. And of course, these parameters, these damage initiation thresholds, completion thresholds, we have to calibrate it using test data. Okay. So it's either this linear softening or ductile, like trapezoidal damage. The other thing is the friction, which there are many ways to introduce friction to the model. Actually, you can even do it indirectly by you can just introduce in this damage law, you can stop it here and then keep the stress constant. That itself will serve to capture this effect of friction, but we did it a little bit more physically, meaningful way. There was a model developed by Raguno for rocks and concrete type materials where they split the total stress into the stress from the damage and stress from the friction. So if D is the damage variable, you can imagine that the stress from the material itself is decreasing with increasing damage. And then there is a friction stress, which increases with increasing damage. And then when D becomes 1, that stress remains constant. So basically this feature captures the fact that stress does not go to 0 when damage is complete. So when D is equal to 1, the stress from the material itself will go away, but the friction stress will always remain. So we adapted this feature in the microplane framework on the cylindrical planes as well as the transverse plane. Okay. So to summarize, basically we take the macroscopic strain tensor, then we rotate it by the angle theta, then we project it onto the microplanes, then we check for the damage. It can either be linear softening or trapezoidal, and check for the friction and calculate the friction coefficients. And using this, we can update the elastic moduli if there is damage. And then using those, we can update the stiffness matrix to get the stress tensor. And whatever is the rotation, it is again updated here. So the system keeps rotating. Okay. Now for some results. So we implemented this as a user material subroutine in Abacus. And these are some of the results. So this is initially single material point evaluation of the model. Uh, you can see maybe at the bottom first, we have out of plane kinking version of the model. In this case, the load was applied as a uniaxial compression in the x direction. And you can see that the application of compression actually leads to local rotation. So compressive loading causes shear. So, and this is a result of only our constitutive framework embedded within it. Okay. Same thing can happen for in-plane kinking. The shear strain is like the 1-2 shear strain. And here it is 1-3. Another thing is you can look at the stress strain plot. It goes up, has a peak, and then decreases but doesn't go to zero, it approaches this friction stress and remains constant. So we have local rotation as a result of compression, and we have combined damage and friction, leading to this kind of stress strain plot where the stress doesn't go to zero. So these essentially are the key features of the Kink band formation. So that's what we now have in the model. And this is one of the predictions of the model with the coupon. We have some test data on out of plane kinking. So on the top left, they conducted a test on on a unidirectional composite. And this is a kink band. The angle is 27 degrees, with respect to the horizontal. And this is then a prediction of our model, pure prediction. This angle is a prediction, and it is 25 degrees, which agrees very well with the observations. So this is a natural outcome from the model. And you can see that the load displacement plot is also consistent with experimental observations, linear, reaching a peak, sudden drop, and then load remains non-zero for a long time. This is out of plane kinking. We didn't have any experimental data on the same material for in-plane kinking, but we kind of enforced in-plane kinking to happen, and we can capture that also in case it happens. But I have to say that under loading, which is aligned with the fibers, the more preferred form is out of plane kinking. At least that's what the observations suggest. Now, the load versus displacement curve for another test set of experiments we modeled. You can see here that these were notched compression tests, and the solid line is from the model and the dotted is from the experiments, and you can see that the agreement is pretty good. In fact, I don't think there are any other papers which show this kind of agreement in terms of the peak, the small drop, which represents the formation of the Kink band, and then this plateau, which shows local rotation, localization of the shear in the Kink band, and frictional sliding in the Kink band. So all these features, our two-scale approach of the microplane modeling strategy, it seems to work very well. And going back to the size effect, which I mentioned, actually the experiments had shown that even this compressive failure, it shows the type 2 size effect type behavior. And actually we simulated it, and you can see that the model also predicts it. So for sure, this is the quasi-brittle failure mode. And if you calculate the fracture toughness from one particular size, it is going to be size dependent. So this for even for kink band formation, this size effect is going to be very important. And we can see that the model can predict and capture the size effect correctly. It obeys the size effect law, and it also matches the test data. Again, this kind of agreement has not been shown in literature by any other model, or they have not even probably checked for size effect. So it's pretty pleasing that it can match this well. Then we did some other studies, sensitivity studies, and essentially we can see that it can capture the effect of misalignment angle. So higher misalignment angles, lower strength. And we also were able to quantify using the model how much effect the friction has on the overall behavior. And we can see that it is actually quite significant. If you run the model without any friction effects, the peak load decreases, the load, after the Kink band also decreases a lot. So the friction in the crack faces plays a very important role in compressive failures, and that also needs to be included in the models. So to summarize the microplane model, it is basically a new formulation. It has two length scales, and it can, basically its hypothesis is that the failure is triggered by interfiber shear in the direction parallel to the fibers. And so it has combined damage and friction. It has local fiber rotation it captures, and so it can do both in plane and out of plane kinking. And it was able to capture very well the failure geometry, the local fiber rotation, the kink band localization, and also this post-peak plateau in the load displacement plot. And most importantly, it was able to capture the size effect. So Of course, this is not a complete model yet, but it has big promise, and it can capture all these features, so it can be potentially applied, to structural applications to predict the failure loads if calibrated appropriately. So which brings me to the next part and the final part of the talk, which is that there are still some outstanding challenges in this approach. So one of the things which is very unclear is what is the fracture energy. We talked about the size effect, but the fracture energy which really governs this kink band failures is not the same as the mode 2 fracture energy. It's a different fracture energy, and we don't know how to characterize it unambiguously yet. But there was some work done by, again, Professor Bazant in the 90s, where he theoretically showed that you can relate the fracture energy associated with the kink band, we call that GB, to the mode 2 fracture energy GF through this expression, where W is the width of the kink band and S is the spacing of these tiny cracks which form axially within the kink band, and they're driven by shear. So in our model, the cylindrical model, we exactly have these kind of axial cracks. Of course, we don't have the spacing. It is all smeared at one material point. But so our model is essentially based on this idea. But this still remains to be seen whether in fact this expression is valid, like from experiments. So the fracture energy relevant to the kink band is still not clear whether it is related to the mode 2 fracture energy by this expression, or is it something else. So this is one open challenge still for us in this area. And the other thing is we only considered uniaxial compression in real applications, like I showed the ocean gate. There is obviously multi-axial compression. And then what happens in those loading situations is more complex. Even in those cases, a kink band develops, but it is like it's neither in plane nor out of plane. It develops at some arbitrary angle in a 3D sense, like try to show it here in this schematic. So it's a 3D oriented kink band, and we are trying to model this right now under general multi-axial loading by combining both in plane and out of plane formulations into one. But this is still a work in progress. And the other thing to consider here is that if there is compression transverse to the fibers, then there is a transverse compressive failure whose mechanism is different from kink band formations. That is like matrix, it's purely matrix shear failure. So that has to be incorporated on top of the kink band formulation. So this is what we are currently working on, but it is a work in progress, not complete yet. And so to summarize, all that I said right now, composites are basically heterogeneous quasi-brittle materials with complex failure behaviors. It's multi-scale, several failure mechanisms which depend on loads and boundary conditions. And so for these purposes, a mechanism-based approach in damage models can be more effective. And so the microplane approach provides a good framework for this. It's a semi-multi-scale framework, allows considering two length scales, the lower length scales and the macro scale length scale. And another point to note is that we have to distinguish between FPZ length, which is related to the fracture energy in the model, and the strength. And there is also the FPZ width, which is necessary in models to get rid of the or achieve mesh objectivity. And so both of these lengths have to be included in the model, or accounted for in the model. And size effect considerations are equally important, and models should be checked for their prediction of the size effect, because if they are only matching one size, there is really no guarantee that they will match other sizes. So at least if we can check three sizes, we can have some confidence in their scaling predictions, and then applying them to larger structures would be more reliable. Of course, there are challenges and limitations, but ongoing work is there to address these. So these are various ongoing areas, in composites technology, but I will probably skip this for now, and I will stop, and I welcome any questions you may have. Thank you.
Thank you, Kiran. It was a wonderful talk. where you talked about all the fundamentals as well as, you took through the advanced formulations for the damage in the composites. I presume that there are some questions from the audience. Let me just go to the chat box and see. So there is one from Professor Mahendra Gattu. He says that in granular soils, we see shear band failure. The soils usually do not have specific direction dependent behavior. How do you justify the hypothesis that fiber buckling causes kink band?
Okay, great question, Professor Gattu. I mean, this is experimental observation actually on fiber composites, that if you load it under compression along the fibers, the local shear in the matrix will trigger the fiber microbuckling. So, I mean, this is not the hypothesis, but that it is an experimental observation that the fibers undergo microbuckling and cause the kink band. Now, your question about soils is very important. Now, in isotropic or homogeneous materials, also under compression, failure occurs only by shear. The compression cannot really cause failure, right? It is just pushing stuff together, but failure occurs by shear. So even for isotropic and homogeneous systems, it is still a shear localization. But that shear localization is probably different from what happens in anisotropic fiber composites, where it is the structure of the fibers which under compression they will tend to microbuckle. So they are related, but not exactly the same thing. I hope that answers the question.
Next question is there. Are you planning to look into the effect of loading rates on the failure behavior? I mean, this is a very valid question.
A very valid question. That's a great question. So, well, I mean, I would like to, if any funding agency is going to support it. So for now, no, we don't have plans of looking at it yet, but perhaps in future, for sure, yes. And that would be very important because we know that there are effects of viscoelasticity of the matrix, which will change with loading rate. And also there are, in general, rate effects associated with any failure. So there are usually higher strengths and higher fracture energies or higher toughness observed at higher rates. So we have to see if that applies true for compressive failures too.
There is next question, which is from Ramlal Priyar. So, who is asking the FPZ length, fracture toughness, and fracture energy are greater for the larger of the three geometrically identical specimens, small, medium, and large, indicating that larger specimens have higher strengths. However, the size effect law indicates that smaller specimens have higher strengths. So please clarify my very fundamental confusion.
Okay, so if you are right, like so, let me open the slide. The slide is visible, right?
Yeah.
Okay, so if you see the definition of fracture toughness, if you just look at the equation, Kc is equal to sigma n times square root d times k alpha. So if you flip it, like if you flip it in terms of sigma n, the d goes on the other side in the denominator. So on the other hand, if you now start from the size effect law, okay, that's probably better. If you start from the size effect law, sigma n is equal to sigma 0 divided by this. So for sigma n, if you substitute the equation for Kc, you can actually see that you will be able to derive this equation for Kc, where if you plot it, there is an increase in fracture toughness with size. So in a sense, the decrease of strength with size is related to the increase in fracture toughness of size. Now, if we were in person on paper, I could have probably shown that you can derive this equation for Kc by starting from the size effect equation. It's fairly intuitive or like straightforward. So if you just substitute for Kc this equation here, so this sigma n will be Kc divided by square root dk alpha, right? So if you substitute that here, and then you solve for Kc, you will get a size dependent law. So that's how the strength decrease is can be directly interpreted as increase in the fracture toughness. So I don't know if I answered the question, but that's how it basically works. And note that the strength is the specimen strength, not material strength.
There's one question from Mayank Agarwal. I think he has typed twice. So he says, what is the role of IFSS or fiber matrix adhesion in the formation of kink bands? And as the failure is due to shear at the fiber matrix interface, that's why friction plays an important role.
Yes, absolutely correct. That's a great question. And in fact, that is one of the crucial quantities. I think if the fiber matrix adhesion can be improved or made more strong, the resistance to failure by kink band will increase. That is at least like hypothesis that if the bond between matrix and fibers is very strong, the matrix will continue to support the fibers more under compression, and so maybe eventually it will still happen, but maybe at higher loads. So yes, that is a very crucial parameter. The only thing is we don't know how to. What we haven't tried is or using this fiber matrix adhesive strength as the parameter in the microplane, because they are not necessarily the same. So in the microplane, we are trying to capture the shear along those cylindrical planes, which kind of includes this effect also in some way. So yes, it is a very important parameter.
Yeah, my own personal question in this context. Don't you think that if we have some nanoparticles added to the matrix, they actually help to improve your, the IFSS?
Yeah, absolutely. So anything that can be done to improve the matrix's resistance to shear damage will help with compressive failure. So bottom line is that the compressive failure of the composite is governed by the shear behavior of the matrix. And so yes, you are absolutely right.
This question from Vikram: what happens in multiaxial architectures? Kink bands presumably blunt when they hit a differently oriented bundle. Does the mechanism of failure change?
And that is also a great question. So what we showed in today's, what we saw today was just a single layer or a laminate with all layers oriented in the same way. Now, if you can imagine a laminate arrangement with layers oriented, differently under compression, then probably the layer whose fibers are most aligned with the loading will experience the kink band, and the other layers will still remain intact and maybe blunt. But hang on, actually, let me go back on that. So the kink band is still traveling within that same layer. So the other layers will not necessarily blunt or stop the kink band, unless if you have multi-axial loading. And if your kink band is like a 3D oriented kink band, then yes, if it is propagating, it has some component of propagation out of plane, then yes, the other layers will presumably stop it. So this basically gives the overall failure a very progressive, progressive nature. So eventually, when one layer is not carrying the load, the other layers will bear more load and then fail by some other damage mechanism. So yeah, I think that's my response.
I think, yeah, there is one more from Mayank Agarwal. In addition to my previous question, if the nanoparticles are added in the system, problem of nanoparticles adhesion with the matrix is a problem in itself.
Yes, that is true. So that is, I guess, all polymer chemistry, and they have to, functionalize it in a way where it is not a problem. Of course, there is dispersion that has to be achieved. Uniform dispersion of nanoparticles is important. But yeah, anything that can be done to improve the shear properties of the matrix will be useful.
Then I had typed in my own question. How do we
Yeah,
handle the impact damage and compression strength after impact using the, the formulations that you have shown?
yeah, that's a great question. We have been asked this question by others too. So essentially, what you would have to do is the compression after impact. Essentially, impact, what it does is it creates delamination between layers.
Yes.
So what you would have to do is model maybe the delamination using some cohesive layers, and then this is a layer level model anyway. So you can still apply the microplane to each layer separately. And once there is delamination, then the model will be able to capture that loss of contact between two layers, and then trigger local compressive failure.
Yeah, but it also happens such that some of the fibers also break, right?
Yeah, that is true. So that
So
that is still not present in the model, of course, but that would involve more of the impact damage modeling.
yes, yes,
So
yes.
that feature is we don't have yet. Now
Okay,
there, under
then
impact, there are many damage mechanisms possible, like fibers can maybe like laterally they will crush. Maybe there are some tensile failures.
right.
Yeah, so yeah, we don't have that yet in the model.
Uh, Another application where I have kind of had this exposure. So see, there are cables made of some of these Kevlar fiber or carbon fibers.
Yeah,
So from the kind of knowledge that you have gained, can I kind of use it for maybe cable with the braiding and all those things to predict the failure?
but under compression, you mean?
It's not under compression, but it is under tension.
Well,
See, sometimes what happens is these cables, they kind of get tangled, and then there is a friction at the interface,
oh, okay,
and then they kind of fail, and then that causes loss of any system that is associated with the cable. So
I
how
see.
do we kind of look at that?
So it is like a fiber bundle of
Yeah, exactly,
cables, is it?
exactly. Yeah.
Yeah, I think for those cases, you would have to probably assume some kind of distribution of strengths in each fiber, like a probabilistic distribution.
Hmm.
And if it is tensile, then individual fiber break modeling of that is quite straightforward. But they all won't have the same strength, right? So
Exactly.
that is one
So,
feature.
I mean, if I
Yeah.
look at it as an individual fiber contributing to the load distribution, somehow it doesn't match with the results that what you get on a, built up fiber bundle and which is
Okay,
braided and whatnot. So it's always found to be lesser than what you would get through any of these models.
I see.
Yeah. And
Well, yeah, I would have to think
wha-
about it. But maybe some microplane could be, developed, yeah,
uh-huh.
for this purpose. Yeah.
Okay, there's one more question. Can we use your findings for fiber reinforced concrete specimen?
Sure, but so in those cases, the fibers are so, I mean, it is different architecture than these composites. So the kink band stuff doesn't really happen under fiber reinforced composites. It is, yeah, so that this mechanism of failure does not happen when fiber reinforced concretes are subjected to compression. So I
Mm.
wouldn't say it is directly applicable to that.
So what are the experimental challenges? I know you have done some experiments too.
Oh
You
yeah,
have used
many
some
experimental
strain
we are
gauges.
doing actually. So we are trying to do this now for woven composites. So
Uh-huh.
in woven composites, the fibers are not straight; they are undulating. So that creates its own effects on the compressive failure. Uh, but one big challenge is stability of the experiment, because the failure under this is quite unstable. So if your specimen thickness is maybe small, you will not even be able to see it. It will either suddenly buckle. So you have to ensure that you use thick specimens, so you can
Okay.
actually see the kink band like clearly. Um, so another thing maybe I can show in the slide.
Hmm.
So these were experiments that we tried to model, right? So they
Yeah.
had to, okay, here. So this they had to create this inclined notch to observe the formation of a kink band. Because now when you have compressive failure, there is another mode that can happen, which is axial splitting, but the splitting goes all the way across the specimen. So if you want to avoid that, to isolate the kink band itself, then you have to do some kind of trick to not have that happen. So what these in these experiments they had to do was to have this inclined notch so that the axial splitting didn't happen and then the kink band developed. So yes, so it is more challenging than tensile failure for sure. There is first of all the stability problem where you have to make sure the specimen thickness is there. Length also has to be adjusted, otherwise it will overall just buckle. So we want to avoid the overall like Euler buckling we have to avoid. And we have these stability issues and isolating the damage mechanism also.
I mean, did you have to use any kind of spherical seating for ensuring it's pure compression during these experiments?
Uh,
Like normally in the case of metals, when I want to do a pure compression test, I would use a spherical seat so that any misalignment in the planes can be taken care of by the spherical seats.
See, actually, no, we have not done that. What there is some fixture called CLC fixture, combined loading compression fixture. So it is a combination of end loading and shear loading. So that is like an ASTM standard for compression tests. So we are using that fixture. We are not using the spherical stuff that you mentioned. But
I mean, I
so just
remember
to
earlier we used to have that, for the this one that IITM RI or something like that, right? The compression fixture, which made strict regulations on terms of alignment and whatnot.
yeah.
Right.
Well, another challenge
Okay.
is like if you do a fracture test, if your initial crack is like thin, what can happen is the faces will just touch each other, and then whatever remain you can't continue with the test. So you have to have a wider notch so that the pre-crack faces don't touch each other during the test. And so there are many these considerations.
Okay, I think I don't know if there are any more questions from the
I had a quick
attendees.
question, Raghu, if I can.
Sure.
So in rocks, sometimes when you have shear planes under compression, you get shear instabilities, but then there will be a mode one which causes it to kink at an angle which is more or less parallel to the loading direction.
Yeah.
Is that sort of thing seen here? Because then the eventual failure, if you have both combined compression and tension in different planes, can still be by tension, but the compression sort of triggers the initial flaw.
Right, you're right. But I don't think these kind of failures have been seen here. So for rocks, the issue is they are very, very brittle under tension. So
Correct.
like they are very strong under compression, weak under tension. So the cracks will prefer, they will, even if they start under shear, they will eventually go to mode one. But for composites, they are very, very strong under tension. So that usually will not happen.
Thank you.
Okay. So if there are no more questions, I think we will thank Professor Kirane for his excellent talk, which covered from fundamentals to the fine print of all these details, and hope some of you will continue to interact with him to gain more insight into his research. And I'm looking forward to listen about this submarine failure analysis and how your theories were able to kind of direct the failure analysis in that direction. So thank you very much, Kirane, for your excellent talk, and we look forward to continued interactions. And thank you all.
Thank you
For
very much
attending
for
this.
inviting
Yeah.
and for all the great questions. It was my pleasure. Thank you.
Yeah.
Thank you.
Thank you. Bye-bye. So Bharti, maybe you can just stop recording. I hope we didn't take too much of your time. The
No, not
morning
at all.
break.